Today we begin our third year sponsoring the Thiel Forums. We're glad you're with us as we continue to feature faculty who are working on special topics of interest, study abroad, or scholarly development, and we welcome our students who are working on projects or who wish to share a particular talent or experience. Please enjoy some refreshments anytime during the presentations. Our first presenter today is in his third year at Thiel as Assistant Professor of Physics. His presentation is titled, How to Confuse People with Mathematics, a topic that many of us may resonate with. As a physics professor, Dr. Torigoe is aware of the importance of integrating both math and physics in his classes. Today, he will focus on the analogy that mathematics is the language of the sciences. I'm honored to present Dr. Eugene Torigoe.
Thank you. All right, so I want to start off by saying that this title is misleading. So I'm not really interested in how to confuse people with mathematics as much as I'm interested in why people are confused by mathematics. And I hope in this talk I'll give you some ideas of some of my ideas on this topic, and also give you some kind of insight into my ideas and research. And whatever kind of nefarious means you use with that information, that's your own problem. So I want to start off by telling you a little joke, and I'll admit that this joke is not funny, but it's a dietitian discusses a meal plan with a mathematician. Okay, so they've gone through the weekly schedule of meals, and then they get to Sunday, and the dietitian says, Sunday is your cheat day. So you can have anything you want, X for breakfast, X for lunch, and X for dinner. And the mathematician shakes his head and says, that won't work for me because I'd never eat the same thing for breakfast, lunch, and dinner. So I'll come back to this kind of miscommunication, but this is the kind of mathematical miscommunication that I'm going to be talking about today. So one of the analogies I'm going to explore a lot in this talk is this analogy of math as being the language of physics. So if you look at Merriam-Webster, one of the definitions for language is a systematic means of communicating ideas or feelings by the use of conventionalized signs, sounds, gestures, or marks having understood meanings. So I knew that Sadie was going to play some music. So one of the, we all know kind of the English language as a type of language, but also another type of written language, the written expression of representation of sound would be kind of like sheet music, right? So physics is a kind of similar kind of thing. It's a written expression of physical ideas, physical concepts, right? So what do languages have? They have vocabulary and grammar. Okay, so these are the definitions of, basically vocabulary are words, and grammar are how you structure the words. They're the rules for construction of words. Okay, so mathematics is kind of similar to these. We have a vocabulary, which are numbers, and oftentimes when we use equations, we actually won't use numbers. We'll use symbols to represent values or numbers. And then we have a grammar, which is essentially addition, multiplication, so forth. Right. So, and I'd say that if you think about it in these terms, mathematics, there's a greater emphasis on the grammar than the vocabulary in mathematics. It's really the, you can understand whether you're in physics or math, everyone agrees on the kind of grammar of how to combine quantities, but oftentimes we use very different vocabularies. Okay? So where does this language as, math as a language kind of break down? It breaks down in the concept of communication. Okay, so primary purpose of languages, spoken languages, and probably also sheet music, is the communication from one person to another. Okay, that's not the primary purpose of mathematics. All right, so mathematics evolved as a system to logically transform equations, which you can think of sentences using kind of a universal grammar. So one way of thinking about it is as if philosophers created their own kind of written language to make logical arguments. That's the primary purpose of mathematics. Communication is a secondary feature of that. And so one of the things that I'm going to talk about today is this idea that because communication is secondary, that leads to a lot of kind of miscommunication with mathematical equations. So let's go back to this math joke that I talked about earlier. So basically, it's a miscommunication because there's a vague meaning of X. All right. So one way of thinking about this is as a mathematical heteronym. Okay, so a heteronym is something where there are two words that are spelled the same way, but they have different pronunciations and meanings. So my favorite example of this is bow and bow. So when I was in middle school, during graduation, we had this thing where they sing this song, "You must have been a beautiful baby." Must have been a beautiful baby, whatever, right? So it has this one part where it says, "You must have had the cutest bow or bow." I still don't know which one it's supposed to be. So that's a kind of heteronym. In this case, it's another heteronym, right? X could have two possible meanings. As the mathematician thought of it, it could have X could be a specific unknown meal, or as the dietitian maybe was thinking about it, X is a placeholder for a particular meal. That's kind of a variable. Okay. So how could you resolve this kind of mathematical miscommunication? Well, what I would do is I would kind of label them with subscripts to say they're clearly labeled as specific meals. And what's interesting about that, I think that clears it up to me. But I was talking to Russ Richens earlier this semester. I told him this joke. I don't know if you remember this or not. And I asked him what he would do, and he gave me a different answer. What he said is he would clearly label them X of t to clearly label them as variables of time. So it's a meal that changed with time. So it's kind of an interesting. So it's kind of an interesting thing. This is how I thought of it, but this is how Russ thinks about it. And actually, it's not uncommon for kind of mathematicians and physicists to have different perspectives on mathematics. Okay, and one of the things I want to kind of make clear is that the math used in math class is different than the math used in physics class. All right, so we train students in math classes for a particular type of skills that they use in physics classes, but it's actually subtly different. What I would say is that there's the same grammar in both, right? Addition, multiplication, so forth, but there's a different vocabulary. All right. So in math class, one of the common things that you'll do is you'll make an unknown x, right? So you have x in an equation, and that's the unknown quantity that you have to solve for. Right? Are you familiar with that? So in physics class, it turns out that we don't have any specific symbols for unknowns. There just are none. Variables, you often see x, y, and z as variables, and here we get this kind of unknown versus the variable confusion here. In physics, we had no symbols for variables. Okay, and then there are constants, and again, they have constants. We use basically the same, but there are some conflicts. Like a can mean a constant, or it could be acceleration. C could be just a kind of general constant, or it could be the speed of light. So there are some conflicts. So one of the questions you might have is, why don't we have specific symbols for unknowns and variables? And the reason is because there's a lot more representational density in physics. So we have to represent things like as variables, unknowns, or knowns, right? So that's the type of thing that we care about. But we also have to represent things like the tidal quantities, or the mass, force, momentum, etc. And so if you look at x, x can't be used as an unknown because x is already being used to represent a position, a distance in physics, right? So if you're using it to represent a position, you can't use it to represent an unknown. Because the distance could be a known or an unknown, or it could be a variable distance. It's really not clear. So we're already using that kind of the x value to represent something else. Also, this value of x could be, we need to associate it with a particular object, the position of the car, or the bicycle, or the person. And they're also kind of, this already have kind of a spatial orientation, but they're temporal associations, right? X at a particular time, the initial value of x, the final value of x. So we're representing this physical information with the symbols, so we don't really have room to represent this kind of information, whether it's a known or an unknown. All right, so that's a particular type of confusion. So when you're solving a physics problem, just by looking at the equation, generally, you will not be able to determine whether it's a known or unknown quantity. Okay? So here's an example of a problem. And one of the things that kind of makes this, I think, comparison very stark is when you compare kind of numeric problems versus symbolic problems, which is something that I've done a lot of research on. So if you have a numeric problem, let's just focus kind of on this middle step right here. You have, let's say, some equation, A, the acceleration is the velocity over time, and then you plug in the velocity and the time, and then you can solve for the acceleration. So what's happening here is a little bit subtle, but what's happening here is essentially you have kind of a general equation, right? And then you plug in the known quantities, and what's left over is an unknown quantity. And then you have kind of the quantity being transformed from an unknown quantity into a particular known quantity of 7.5 meters per second squared, right? So the equivalent to that is if you were to do this problem symbolically. Essentially, all of those transformations occur kind of on kind of a mental level. You're basically doing that implicitly. Any transformations between known and unknowns, you have to kind of carry in your head. And so what before were 3 separate steps kind of condenses. Now, if you understand and you can kind of track this information conceptually, then this is a much nicer compact notation. But if you can't do that, then it's just confusing, right? So again, this is the idea that mathematics and physics has not been evolved for communication. It's not to make it clear to other people what you're doing. It's a system to kind of logically track information, right? So as long as the person using the mathematics can understand it, that's the primary purpose of the equation, right? And there's also this other thing over here. When you're solving symbolic equations, you can have quantities that represent like different points in time. So here, there's a velocity that corresponds to a different time than this other quantity over here. So this velocity doesn't necessarily correspond to that time. So there are different weird things like that can happen in equations. So I'll just tell you, there's a physics problem. I'm not going to ask you to solve this. But when I was a graduate student, this is one of the problems I did research on. And I went to a big school. We had about 1,000 students in our introductory physics class, so it was big. And what we did is we gave 2 different final exams. One had this version of the problem. So it's a car can go 0 to 60 meters per second in 8 seconds, and what distance d from the start and the rest of the car traveling 30 meters per second. And it's the same, what we gave on another exam, kind of randomly administered, was the same question, except instead of numbers, we just gave kind of v1. Instead of 8 seconds, we get t. And then instead of 30 meters per second, which is half of 60, we get v1 over 2. So it's basically the same question. This first one was very easy. People had no problem doing that. Maybe if you took an introductory physics course and you studied for your final, that wouldn't be so difficult. But when you gave them the symbolic version, with just numbers replaced, the average dropped by half. So this is a very interesting problem. There's a lot of weird stuff that is kind of going on in here. But essentially, one of the main issues is the fact that students have difficulties identifying kind of the meaning of v as either kind of a variable or whether v corresponds to one time or another. And so there are lots of confusions related to actually what those symbols mean that lead to this kind of error. So why don't we just have a more detailed vocabulary so that these communications don't occur? Well, one of the primary reasons is because the purpose of the math is to to make logical argumentation. So one of the ways we do that, and when you're solving problems, one of the ways you can check that is with something called limiting cases. So you solve a particular problem, right, with specific unknowns, but then what you do is you imagine those quantities as being variable. So you can imagine like varying different quantities in the problem. So it no longer relates to a specific situation, but to more variable situation. And so here's an example of, this is a very kind of simple example of this, but you have a block that's kind of sliding down a ramp, okay? So if you solve for the equation for its acceleration, it's this quantity. G is the acceleration due to gravity times sine of the angle of the ramp, okay? So one of the nice things you can do about this form is that you can apply limiting cases. So you could say, what would be the acceleration of this thing if this theta were 0? And theta 0 would basically correspond to being perfectly flat. And we'd expect that A would be 0. And if you plug in theta equals 0, you get 0. So that makes sense. That's a way of checking the equation. Or what would happen if it were 90? If it were 90, then this would just be straight up and down. So it would be falling straight down. So it should fall at the rate of gravity, right? And that's what happens. If you plug in sine of 90, that's 1. So just the acceleration equals g. So you can imagine these equations can get more complex. But this is kind of a system that allows you to check equations. So what you give up to have this sort of system is you give up the kind of more specific labeling of quantities, right? So you can kind of, yeah.
If I was a philosophy student, I would say that, well, at 180 degrees, it falls at twice g.
Yeah, that's right. That's right. So there's certain applicability that you can have for this, but that would be correct. So you have to know enough physics to kind of know what the limits are of this thing. So, in summary, math is a peculiar type of language. I think it's very similar to, it follows a lot of the same rules that you would expect from other languages, except that communication is a secondary component of its evolution. And so I think what happens is that leads to a lot of miscommunication between people about math. And so math in math class is different from math in physics class. And that symbol usage is sometimes purposely vague when used in physics. But the purpose of that is to give it more flexibility and utility. So thank you.